atoms and elements. Elements are the pure substances. So if you take any block of a substance, any type of matter, and we try and chop it into smaller and smaller pieces, like the tiniest pieces that we get, that basically is what is called as an atom. So every matter, every element is basically a pure substance. Every element is a pure substance, and it is made up of tiny, tiny, tiny particles that are called as atoms. By definition, atom would be a smallest particle of an element that would retain the characteristic of that element. What that simply means, if I take this aluminum foil and I chop it up until I get to like these smaller size particles, then this is called atom, as long as this is still behaving like aluminum. So this is aluminum, it has its own properties. For instance, it's a metal, right? Similarly, if I can divide it into these tiny particles that still have the same chemical properties like aluminum, then we would call that an atom. You could go even smaller than an atom, but then it does not retain the properties of aluminum anymore. So the smallest particle that still retains the characteristics and properties of that element, that is called as an atom. There are multiple chemicals around us, and all those chemicals are represented by some chemical symbols. What are these symbols? These symbols represent basically the names, and a lot of times they also have an abbreviation to them, and those abbreviations are usually either a one letter or a two-letter word. Okay, most of the times it's a one-letter word. A lot of times these chemicals, their first letter of their name is basically the symbol that is used. For example, carbon is C, nitrogen is N, fluorine is F, oxygen O. But sometimes some of these elements are represented by a two-letter symbol. In this two-letter, the first letter is always written in capital and the second is always written in lowercase. So cobalt is CO. It's not C because C is already taken by carbon. Calcium is Ca. Aluminum is Al. Magnesium is Mg. So these are two-letter abbreviations that are also used. Here are some common elements and their symbols that are used. Some of these elements you should definitely become, and with their symbols, you should definitely familiarize yourselves with these because you see them around you. Aluminum, you should know that basically is Al. Copper is Cu. It's not Co. Co is cobalt. Copper is Cu. Okay, why is it Cu? Some of these are pretty easy. For example, aluminum Al, argon Ar, barium Ba. Usually their symbol is coming from their name, the first two letters, but that's not true every single time. For example, arsenic is not Ar, it is As. Calcium Ca. Cadmium is not Ca. Why? Because Ca is taken by calcium. So cadmium is Cd. So there are some names where your letters, the symbols that are used, the letters do not match with the name. Okay, then there are some ones which are completely different from their name. For example, sodium. Where is it written? Do we have it here? Right here. For example, sodium. Sodium is written as Na. There is no N in the word sodium, but it's still written as Na. Why? Because it comes from its Latin name. It was called as natrium, so it's called as symbol as Na. Silver is Ag. Okay, it comes from its Latin name argentum. Potassium has no K in it, but it's written as K, so it comes from its word kalium. Okay, so there are some which have no similarity, their symbol has nothing similar with their names, but please remember some of these common elements, even though their symbols and their names basically just don't match. Okay, now coming to periodic table. So this is the periodic table. It has every single element listed. Every single element is listed on this table, and this table basically is called as the periodic table. This table is kind of like the holy grail for chemistry. Just by looking at the location of the element, for example, sodium is located here, magnesium is located here, calcium is located right here, we can tell a lot of information. We can predict several properties of these elements just by knowing where they are located on this periodic table. Every element has a specific position on the periodic table. This periodic table, the first periodic table that was made by Mendeleev. That was in 1800s. He created a periodic table by increasing the atomic mass. So he arranged his elements in an increasing order of atomic mass, meaning the smaller mass elements came first, followed by a heavier element. But that periodic table worked for a while. He was able to predict properties of some elements, but that did not work as we discovered more elements over the years. So now what we use is called as the modern periodic table. So this periodic table that you see right here is the modern form of the periodic table. Here the elements are arranged in the increasing order of their atomic number. What is that atomic number? We'll talk about it later on. But remember, the first periodic table that was made was based on the mass, and now we have changed it to atomic number. Not now, it has been years, but the new modern periodic table is based on atomic number. And then, for instance, the periodic table right here, this number that you see on top, 1, 3, 4, these are atomic numbers. How do you read a periodic table? A periodic table is basically like a calendar. So when you read a calendar, you usually go like this: 1, 2, 3, 4, 5, 6, right? You go left to right, and then you keep going to the lower rows. Same thing. We go from here left to right, and then we come back down to the next row, left to right. We come back down to the next row, left to right, come back down to the next row. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So for instance like these, you can see that the numbers are increasing, and this number is the atomic number. So it's arranged in this order now. How is this periodic table divided? The periodic table is majorly divided into rows and columns. The columns are called as groups. It's called as groups, or they are also referred to as families. So all the elements that have very similar properties, they behave very similar to each other, they are arranged in a family. They behave like a family, they have very similar behavior, similar properties. That is why they are arranged in a family, which is a column, and it's also called as a group. They belong to the same group. For example, this is group number 1, or it's also called 1A. Group number 2 or 2A. Group number 3, 4, 5, 6, so on and so forth. We have 18 groups in total. Okay, some of these groups are called as A. For example, this is 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, and this in the middle, these are called as B. So this would be called as 3B, 4B, 5B, 6B. So this is how we divide the columns. The rows are basically called as the periods. There are 7 periods in the periodic table, which is basically the arrangement of elements in different rows. Again, these are the groups, columns. Now we'll look into further categorization of these elements arranged in the periodic table. First category is this: we can divide all these elements into 3 different categories, which is metals, non-metals, and metalloids. Okay, what are metals? All these elements that you can see in the color blue, these are referred to as the metals. Metals are all arranged in the left part of the periodic table. So metals basically are the left part of the periodic table. Left basically just means, for instance, you don't have to memorize it. For example, we know iron. Iron is Fe, and we know iron is a metal. Where is it arranged in the periodic table? On the left side. Another element, common one, is copper. Copper is Cu. Zinc, Zn. Silver, Ag. All of these are metals. They are on the left part of the periodic table. All the non-metals are on the right side of the periodic table. So all these in the green. Only exception to this is hydrogen, which is also a non-metal, but it's arranged in the left part of the periodic table. But all of these elements that you see in the green, these are non-metals. And these elements in the middle, these are called as the metalloids. They are metalloids. or they are also referred to as the semi-metals. So their properties are somewhere between the metals and non-metals. They are not metals, not as good as metals, but they're not as bad as non-metals. Okay, so their properties are somewhere in the middle. That's why they're called as metalloids or semi-metals. One very easy way to remember this distinction on the periodic table is you can basically create this kind of a ladder. Okay, and all these elements are arranged around this ladder. All the metalloids are arranged in this ladder. Okay, and all of these apart from this ladder, these are non-metal. So you should be able to recognize if an element is a metal or a non-metal just by looking at the location. What are their distinctions in properties? So all of these are metals. Metals are on the left hand side of the periodic table. They're usually solid at room temperature. These are some properties that we know actually. They can be molded. They are into different shapes, right? They can conduct heat, they can conduct electricity. Those are the metals, properties of metals. We'll talk about transition and inner transition later on, but basically these are all the metals. Then we have next category, which is non-metals. The non-metals are on the right side of the periodic table. Their physical properties vary a lot, and they basically are not conductors of heat and electricity, or you can say non-conductors of heat or electricity, and that is why they are called as non-metals. And then we have metalloids, located somewhere in the middle right here, like a form of a ladder. Okay, they are semiconductors. They do conduct electricity, but they do not do it as efficient as metal, so that's why they are called metalloids. Then there's also another category that is used for categorizing these elements in the periodic table. The first of this is all these elements that we saw in A group, 1A, 2A, 3A, 4A, 5A through 8A. All these are called as main group elements, or they're also referred to as representative elements. Either or, but these are referred to as representative or main group elements. These elements that you see in the middle, all of these B group elements, this is 3B, 4B, 5B, all of these B group elements are called as transition elements. These are transition elements. The two other rows that you see in the very bottom, these are called as inner transition elements. Apart from this, the top row is called as the lanthanide series, and the bottom row is called as the actinide series. This comes from the first element that you see here. This is lanthanide, this is actinide, so they come from these names, lanthanide series and actinide series. So just know these distinctions. Apart from this, there are also some common names that are given to different groups in this periodic table. Why? Because they have very similar properties. So all the group 1 elements, they behave very similar except of hydrogen. Hydrogen's an exception here. Except that every other element behaves very similar. For example, all group 1 elements are very, very reactive. They aggressively react with water. Okay, so they have very similar properties. That's why they are given a common family name, just how we have usually a family name. Elements in the periodic table also are given some family names. So this family, group 1, is called as alkali metals. Group 2 are called alkaline earth metals. These also have very similar properties to each other. Group 8 are called as noble gases. Noble gases also are referred to as inert gases. What this simply means is that they are inert, they're very noble, they are very stable, because of which they do not react with anything else. That is why they are called as inert. Example is helium, neon, argon. These gases do not react with anything else, and that is why they are noble or inert gases. The group number 7A, this is also called as halogens. These are also very reactive elements. These are referred to as halogens. So this is alkali, lithium, sodium, potassium. Like you can see here, they react very explosively and very aggressively with water. Then we have alkaline earth metals, all of these, they also have very similar properties. Like you can see, they also look pretty much similar, right? They're very shiny silver, so they have very similar chemical and physical properties. Then we have these halogens, which also you can see right here, they would have very similar reactive properties. Okay, noble gases, they are very inert, they do not form any compounds, and most of these are gases at room temperature. So that is basically a summary of our periodic table. You should be able to recognize this. These blue ones are metals, this is non-metals, these are the names written on them, these are the group numbers written on them. So please use this periodic table as a reference for every single time that you're doing any questions. These are representative, transition elements, lanthanide series, actinide series, and then there are also some names, common names given to some other groups. Let's try some questions. For instance, very direct question. Identify the element described by these following groups and periods. Group number 7A, period number 4. So we go to group 7A, which is this right here. Oh, sorry. Group number 7A right here. Period number 4 is going to be this. So we drag it down and we can see the element that exists is Br, which basically stands for bromine. So this would be the correct answer. So that's how you can figure this out. Group 2A, period number 3. So we go to group 2A, which is basically this. So this column, period number 3 is this particular row. So the element that exists is Mg, which is magnesium. So you should be able to recognize the groups and periods on a periodic table. Next question, identify the element as metal, non-metal, or metalloid. Again, you need a periodic table for this. Sodium, find sodium is Na, which is right here. It's on the left side of the periodic table, so it's a metal. Then we look at chlorine. Chlorine stands for, the symbol is Cl. Cl is right here on the periodic table, and that is on the right side, so this is a non-metal. So that's how you can recognize the elements as metal, non-metal, or metalloid. You should just recognize this periodic table. So starting now, please keep this periodic table handy and try and get familiar with where some of these elements are located on the periodic table. Next, we'll move on to atomic theory. So we'll try and learn about atoms now, their structure. The first theory that was given regarding atoms was given by Dalton. John Dalton gave a theory which we call as Dalton's atomic theory. This was the theory that was proposed very early on in the 18th century, and here are some of the propositions that he basically gave, some part of his proposals. His theory simply said that all matter is made up of tiny indivisible particles called atoms, which is correct. All the matter is made up of atoms, except one wrong thing that he mentioned was that atoms are indivisible. We do know atoms can be further divided into smaller particles now called the subatomic particles. We'll talk about this later on in detail, what are subatomic particles, but this was the only part in his theory that he mentioned which was wrong, which we have proved wrong now. But at that time, what he said was everything's tiny, made up of tiny indivisible particles. He said all the elements have atoms which are very unique to each other, which is true. For example, this simply means hydrogen atom is different from oxygen atom. They're completely different from each other. Atoms of two or more different elements combine in a fixed ratio to form compounds, which is also true. For example, atom of hydrogen and oxygen, they will combine in a ratio of 2 hydrogen atoms and 1 oxygen atom, and they will give you a compound which is called H2O, which is water. So that's a compound, which is also true. They always combine in this fixed ratio. He also mentioned that during a chemical reaction, atoms get rearranged, separated, combined in different orders. They can never be created or destroyed in a chemical reaction, which is also true during a chemical reaction. For example, if H2 plus O2 gives us H2O, if I balance this reaction out, we need this much. So what you have here is we have 2 times 2. You don't have to know this for now. We'll learn about this later on. But basically, in this reaction, we have 4 hydrogen atoms, 2 oxygen atoms. Initially, hydrogen atoms are just combined with each other, oxygens are just combined with each other. And then at the end, we still have 4 hydrogen atoms here and 2 oxygen atoms here. But now this hydrogen and oxygen is combined with each other. So they have rearranged with the atoms have gotten rearranged, but we still have not lost any of the atoms. Now let's look into how were the further details about the atom and its structure were discovered. So to understand that, the first thing that we need to understand is about the electrical charges. So remember, in case of electrical charges, the two opposite charges would always attract each other and the like charges would always repel each other, which essentially just means that if we have 2 positives or 2 negatives right next to each other, because they have similar charges, they would always repel each other. Whereas if you bring a positive and a negative next to each other, they would always attract each other, so they'll pull each other towards themselves. Based on this, the first time J.J. Thomson was able to discover what we now call as electrons. He discovered cathode rays, and he found that these rays are basically small negatively charged particles which are called as electrons. So Thomson was the first person to figure out that atom consists of something negatively charged, and based on this, because all the atoms we know are neutral means that they have 0 charge, so he discovered that atoms consist of something negative, which means there has to be something positive in the atom to cancel each other's effect, and that is how your atom becomes neutral. So based on that, he gave a model which is called as the plum pudding model of an atom, and he said that an atom consists of several negatively charged electrons which are distributed randomly, and they're randomly scattered throughout an atom, and the rest of the space of this atom is all positively charged. So basically, just how if we have a plum pudding or a chocolate chip cookie, in that case the chocolate chips are located scattered anywhere randomly in that cookie dough. So that's the same thing. His theory was that that is the structure of an atom. It's negatively charged electrons scattered randomly in a positively charged atom. Later on, Rutherford was doing an experiment. His experiment is popularly called as the gold foil experiment. He was doing a completely different experiment, not interested in atom structure or anything, where he took a very thin foil of gold and he took a source of some particles. These were positively charged particles, and he arranged this gold foil and he arranged a detector around the foil. So when these positive charged particles will hit the detector, he would be able to notice where they got. So when he did this experiment, he noticed that a lot of the particles that he shined on this gold foil went straight through. Some of them got deflected at an angle, whereas some of them got deflected at a certain different angle. Okay, based on this, he proposed that he thought of the atom and he thought of Thomson's model, and then he proposed that actually Thomson's model probably is not true. He mentioned that because a lot of his particles went straight through like this, a lot of his particles went straight through the gold foil, most of the space around the atom is empty. Second thing, he proposed that some very few of his particles went and they were deflected back at an angle. And because his particles were positively charged and because they are getting deflected by something, that means that part is also positively charged. So he proposed that inside an atom there's a very dense part which is positively charged. Not all of the atom is positive. There's a very dense small portion which is positive, and some of these particles were deflected away from it, which means this part, because it is positive, when the particles were coming closer to it, they were repelled by it, so they deflected away from it. And that's when he proposed another structure of an atom, and he said that there must be a small dense positively charged nucleus inside of an atom that deflects the positive charged particles that come close to it, and there's a region of space surrounding the nucleus that is occupied by the electrons. So Rutherford's theory is completely different from Thomson. Thomson said everything's positive and then there's some negatives scattered around, whereas Rutherford said that everything is empty. There's a very small part which is positive, and this empty part has some areas where the negatives are located. So based on all the theories, and there were some more models provided later on by Bohr as well, based on that, now we have a final structure of atom until which basically tells us that an atom consists of a nucleus. So very center is a nucleus which is positively charged. It has the positive charged particles, and around it we have a lot of empty space where we have electrons in the space, and these electrons are negatively charged. And what is present inside the nucleus are two things. The nucleus consists of positively charged protons and neutral neutrons. Neutral basically means it has zero charge. There is no positive or negative charge, it is zero charge, and that is the structure of the atom that we now hold true. So these are particles that you see inside of an atom is called the subatomic particles. And now this basically tells you that Dalton's theory, which said that the atom is indivisible, why it is not true, because it can be divided into protons, neutrons, and electrons. So these are the particles. The symbols you can see right here. Proton is usually written as P or P plus because it has a positive charge. Neutrons are N or N0. Electrons are E with a negative charge. Charge is positive 1 on a proton, negative 1 on electron, and neutral on a neutron. Where are these located? Protons and neutrons are located inside the nucleus of an atom, whereas electrons are located outside the nucleus of an atom. So please remember this chart. Last thing is the mass of an atom. Okay, because atom is really tiny, okay, in very small size, usually when we talk about mass of an atom, it's written in a different unit which is called as AMU, which stands for atomic mass unit. Now the mass of the atom all of it comes from the nucleus. The protons carry a mass of around 1 AMU, so approximately 1 AMU. Mass of neutron is also 1 AMU, whereas mass of electron is, you can see, 0.0005, which is basically almost 0 AMU. So most of the mass is contained inside the nucleus by protons and neutrons, and electrons are very negligible in mass, and that is what is atomic mass unit. It is just a different unit that is used when we are describing mass of atoms. Okay, now there are some other numbers that are usually used to represent elements on a periodic table. The first of that numbers is called the atomic number. It is also abbreviated as Z, the alphabet Z. Where do you find the atomic number? On the periodic table, we saw that every single element on the top, there's a number written on every single element. This is the number. For example, in front of sodium, the number that is written is 11. That is the atomic number of sodium. Okay, every element has a specific number attached to it. So the important thing to remember here is atomic number is basically the identity of the element. We cannot change the identity of the element. Every element has a specific number, and that is called the atomic number of that element. For example, if you find sodium anywhere in this universe, the atomic number will always be 11. And what does this tell you? The atomic number is always going to be a whole number. First thing, it's never decimals or integers. It is equal to the number of protons in an atom. So it tells you how many protons are present. So sodium has how many protons? Sodium has 11 protons. That's what it tells you. For example, carbon, if you look at periodic table, carbon is number 6, which basically tells you carbon has 6 protons. Copper, right here, copper, if you find on periodic table, is number 29, which means it has 29 protons, so on and so forth. So this number right here tells you how many protons any element has, and this is the identity of the element. This never changes. Now, because atoms are neutral, how do you know it's neutral? If an atom has a charge on it, sodium is usually written like this. Okay, if it has a charge, it would always be written on the top right corner. For example, Cu 2 plus, oxygen 2 minus, it would always be written on a top right corner. And now these are not called as atoms. When they have charge, they are called as ions. Okay, so if they are atoms, they are always going to be neutral. There will be no number written on the top right corner. That simply tells you it is a neutral atom. And now, because we know, for example, we saw sodium has how many protons? It has 11 protons, which means it has positive 11 particles in it. Because it is neutral, you need the same number of negative elements to neutralize this charge. You need the same number of negative. That is why the number of electrons in an atom is equal to the number of protons as long as your atom is neutral. Okay, so number of protons is equal to number of electrons as long as it is a neutral atom. Remember that. The next number that is commonly used is called the mass number. It is abbreviated as A. Okay, what is mass number? The definition of mass number is it is equal to number of protons plus number of neutrons. It tells you how many particles are present inside the nucleus. Again, this is also a whole number, and the important thing is this is not written on periodic table. You will never find the mass number written on periodic table. If needed, it will always be provided in a question. Mass number can change for different atoms. Same element can have atoms with different mass numbers. So it's not a fixed number for any element. It can change, and that is why it's not listed on the periodic table. But basically what it tells you is atomic number is equal to number of protons plus neutrons. So if I know how many protons I have, I can find how many neutrons are there by doing atomic number minus protons. So if I rearrange this equation, that gives me this. Number of neutrons is mass number minus protons. Or you can say number of neutrons is atomic number minus the mass number. Example, a question like this: use a periodic table to fill the atomic number, number of protons, neutrons and electrons for each of these elements. For example, sodium atomic number is what? It is 11. So number of protons is also 11, and number of electrons is also 11 because it is neutral. Zinc, if you find zinc on the periodic table, it's right here. Atomic number 30. So number of protons is 30, and number of electrons, as long as it is Zn, it is also 30. Sulfur, if you go on periodic table, right here, 16. So atomic number 16, proton 16, electrons also 16. Now there is something that is referred to as the atomic symbol. This is the way we represent any element from the periodic table. Every element is written using this symbol, atomic symbol. How is this written? For example, like this. Magnesium tells you that the symbol of the element. This element we are talking about is magnesium. Mass number is always written on the top left corner, and atomic number is always written on the lower left corner. So usually if this is the symbol, I will write it here. If this is the symbol X, the atomic number is always written right here, which means this is my Z and this is the A. This is always the mass number and this is always the atomic number. Okay, for example, like this, magnesium, that means magnesium has how many protons? Protons is 12, and protons plus neutrons is 24 based on this. This number again is not given on periodic table. Sometimes it's also written like this. For example, if I say H1, that means this number that is written 1, that is the mass number of the element. I can also write magnesium 24 like this, magnesium 24. That means this number that is given to you is the mass number. Why is that? Because atomic number you can also find it from periodic table. So we usually write mass number. Atomic numbers are usually avoided because you can find it on periodic table. So every element is basically written like this. Helium has mass number here, atomic number here. For example, if I tell you helium, if I give you a symbol of helium like this, 2, 4, then you can tell me that the number of protons is 2 because this number is 2, and number of protons plus neutrons is 4 because this number is 4, which means neutrons will be 4 minus 2, which is 2. So it's very easy. You take this 4 minus 2, top number minus the bottom number, that gives you number of neutrons. Example like this, an important isotope of uranium has 92 protons, 143 neutrons. Write the symbol with atomic and mass number. uranium, it says atomic number, protons is how many? 92, which means atomic number goes right here, and mass number is what? Protons plus neutrons. Protons is 92, 143, total will be 5, 3, 235. So 235 U92. That would be the symbol for uranium 235. Right, continuing. There are more examples, so please try the examples that are given to you in the slide, and if you have questions you can ask me about it. The next topic is isotopes. Okay, what are isotopes? Isotopes are basically the atoms of the same element that have different mass numbers. Like I mentioned, sometimes some elements can have different types of atoms and their mass numbers will be different. For example, magnesium. Magnesium is what? Mg. If you look at periodic table, atomic number is 12. Atomic number for magnesium will always be 12. We cannot change it. But you can find magnesium as magnesium 24, magnesium 25, or magnesium 26. And what are these numbers? 24, 25, and 26. These numbers are their mass numbers. These atoms, when you have the same element, atom of the same element, when they have different mass numbers, those are called as isotopes. So that is the definition of an isotope. Atoms of the same elements with different mass numbers. That simply means they have same number of protons because all of them are magnesium 12, but they have different number of neutrons. For example, like this: magnesium 1224, 1225, 1226. Their protons in all of them is 12, 12, and 12. But if you look at neutrons, is how many? 24 minus 12, 25 minus 12, 26 minus 12. So neutrons is the only thing that is different in them, and those are called as isotopes. Most of the elements that you see on periodic table, they have multiple isotopes. Most of the elements. Example like this. Let's try a question. There are 3 naturally occurring isotopes of carbon: carbon 12, carbon 13, carbon 14. 12, 13, and 14. Write the symbol, protons, neutrons, and electrons for each of these. So symbol for the first one, carbon 12, 12, carbon 13, carbon 14. Remember, mass number goes on top. And because this, if you look at carbon, carbon is atomic number is 6. So all of these would be 6. Number of protons, 6. Number of electrons, also 6, because they are all neutral. So electron is same as protons. And neutrons will be 12 minus 6, which is 6. 13 minus 6, which is 7. And for this, 14 minus 6, which is 8. So in all of these cases, proton is same, electron is same. Only thing that is different is number of neutrons, and those are called as isotopes. Another thing you'll find is the atomic mass. So what is the atomic mass of an element? This number that you will see on periodic table, that's written under every single symbol of an element, that is called the mass of an atom. Okay, that is called the atomic mass of an element. This is the mass of the atom of an element in AMU, which means what is the mass of one sodium atom? One sodium atom weighs 22.99 AMU, atomic mass unit. Where are we getting this number from? This number is called the average atomic mass. This is the average mass of every single isotope of sodium that exists in nature. Okay. How do we find the average atomic mass? This is the formula for average atomic mass. Average atomic mass is percent abundance times the mass of the isotope plus percent abundance of second isotope times the mass of the second isotope. If any atom has 3 isotopes, you will add another one plus percent abundance of the third one times its mass of the isotope 3. If you have 4, you can keep on going like that. Percent abundance times the mass. What is percent abundance? Percent abundance simply means how much percentage of a mass of a substance is occupied by that isotope. For example, carbon atoms exist as 2 isotopes. Carbon 12, the mass of the atom is this much, and this is its percent abundance. And carbon 13, so there are 2 isotopes, carbon 12 and carbon 13, and these are the masses of each. Why are the masses different? Because they have different number of neutrons. And remember, in case of an atom, neutrons carry almost 1 AMU of mass, so neutrons are heavy. That is why their atomic mass is different for each isotope. And this is a percent abundance, which means if I take a block of carbon from somewhere, 98.9% of that carbon is made up of carbon 12, and only 1% is made up of carbon 13. So this is telling you how much of a substance is made up of. So like 99% is carbon 12 and only 1% is carbon 13. So we have to take an average of both of these atomic masses, and that would be the mass of the atom. How do I find it? Use the formula. So average mass is going to be percent abundance of first one, which is 98.93, but because it's a percentage, we will divide it by 100, because we can't use a percent in the calculation, times 12.000 U AMU. U also means is an abbreviation for AMU. AMU is same as U, plus the second isotope, which is 1.07%, but divide by 100 because it's a percentage. We have to convert it into a fraction. 13.0034 U. You multiply these two, divide by 100, and plug that into your, add it together and plug that into your calculator. So this is going to be 0.9893 times 12.000 in parentheses plus 0.0107 times 13.0034 in parentheses, and solve it, and that would give you your final answer in U. But the important thing to remember here is, please use your calculator correctly. Make sure you put this in parentheses plus this in parentheses, otherwise your calculator will not give you the correct answer. So please make sure you use the parentheses correctly in your calculator, and that is called the average atomic mass. The final answer I have is 12.01 AMU. So this should give you 12.01 AMU. Another example is right here. Naturally occurring copper consists of 69.17% of copper 63, which has atomic mass of 63.9396, and 30.83% of copper 65, which has the isotope mass of 64.9278. What is the atomic mass of copper? Again, the average mass will be percent, which is 69.17 divided by 100, which will give you 0.6917 times 62.9396 plus 0.3083 times 64.9278. Plug this into calculator exactly like this with the parentheses, okay, and that should give you a final answer. Remember the percentage, you take your percentage and you divide it by 100 every single time. You can't just put percentage and include it in general format. You have to convert it into normal decimal numbers. And the final answer is 63.55 AMU. The next topic is ions. What are ions? Ions are basically charged atoms. When atoms carry charges, they are called as ions. Why do atoms carry charge? During chemical reaction, whenever there is a chemical reaction, during chemical reaction, atoms will either gain electrons or they lose electrons. Okay, and only electrons are participating, which means when you take an atom, the nucleus, which has protons and neutrons, this never participates. Only electrons participate in a chemical reaction. So atoms can only do one thing, which is either they lose electrons or they gain electrons. They will never change the number of protons or neutrons inside. And whenever an atom gains or loses electrons, the number of protons, we said, is equal to number of electrons. But if it loses one electron or if it gains one electron, then this is no longer true. That's when atoms get charges. They get either a positive charge or a negative charge. How do they get it? For example, sodium was Na. How many protons does it have? 11. Atomic number is 11. How many electrons does it have? Also 11. But let's say it lost one electron. So now the number of electrons is how many? 10. Because it lost electron, an electron carries a negative charge, it lost one negative charge, which means how many protons does it have now? Still 11. So it has positive 11 charge and it has negative 10. So overall the charge of the sodium is +1. And that is when sodium basically has a charge, and then this is not called a sodium atom, this is a sodium ion. That is how sodium gets a +1 charge, because it lost electron. So remember, whenever an atom loses electron, it gets a positive charge because it has, the electron is gone, the negative charge is gone. Another example is here, oxygen. How many protons does oxygen have? 8. How many electrons does oxygen have? Also 8. Now oxygen gained 2 electrons, which means how many electrons does it have now? 10. How many protons? Still 8. So it has 8 positives, but it has 10 negatives. 10 negatives, which means the negatives are more. So overall, oxygen will carry a 2 negative charge because it has 2 extra electrons. So whenever an atom gains electron, it will carry a negative charge. Always remember that. Loses positive, gains negative. Okay, which brings me to the next part. I kind of wrote on all of it, but basically ions are what? It's an atom or group of atoms with an overall charge. The positively charged ions are called as cations, and the negatively charged ions are called as anions. Okay, it's very easy to remember. Anion basically is a negative ion. A negative ion is anion, anion. Okay, cation. Remember how cats have paws, right? So cats positive, so it's called cation. Cation are positively charged. That's how I remember it. A negatively charged ion is anion. Example like this: sulfur is atomic number 16. Sulfur atoms commonly form sulfide ions, which have a charge of -2. How many electrons are in the electron cloud of sulfide ions? So sulfur has a charge of -2. So question is asking how many electrons. First, if it was S, the number of protons is 16. How do we know it? From periodic table. Number of electrons would also be 16 because it has no charge, but because it is S2 minus, proton is 16, it has gained 2 extra electrons, so it becomes 16 plus 2, 18 electrons, and that would be your final answer. So remember, for every positive charge you lose electron, for every negative charge you gain electrons. Let's try a few more examples. For example, F minus. How many protons, electrons are in each of the following? F minus. F is where? Right here. The number for F is 9, which means protons is 9. Electrons would also be 9 if it was F, but it is F minus, which means it has 1 extra electron. So 10 electrons. Negative charge means it has extra electrons. Magnesium 2 plus. Magnesium is right here. The number is 12. So protons is 12. Electron would also be 12 if it was magnesium, but it is Mg 2 plus, which means it lost 2 electrons. So minus 2. It also has 10 electrons. N3 minus. N is right here. So 7. Proton is 7. Electron is 7 if it was N. But it is 3 minus. So it has 3 more negative ones. 10 electrons. W6 plus. So same thing. You keep on. You can find charges from any of these elements. The important thing to remember here is the number of protons is given by this number on top. The atomic number, that never changes. The number of electrons on a neutral atom would be this, but it would change if you add or you remove the electrons from it. So if it's a positive charge, you subtract the electrons because it has lost electrons. If it's a negative charge, it has gained electrons. So you add the number of electrons. For example, W is right here. W is 74. So protons is 74. If it was W, electrons would also be 74. But it is a positive 6, which means it has lost 6 electrons. So it would be negative 6. 68 electrons. That would be your final answer. And that is atoms, elements, and periodic table, and some of the information about ions.